Hello. I wanted to introduce the idea of the Analyzing Data Lab. This is a lab a lot of people have difficulty with, even though it's really a very simple lab. In a lot of other science classes, you are introduced to the idea of significant figures. We talk about significant figures here too, but we talk about them not just in how do you manipulate numbers that you already know the significance of, but how do you figure out what the significance is to begin with? So you make some measurements. Okay. Now, if you already know what the significance is, that this number has so many significant figures, that number has so many significant figures, and so forth, you know the rules for adding them, subtracting them, multiplying, and dividing them. That's in the lab. These are the same rules everybody else uses. But the question is, how do you figure out how many significant figures to start with? If you're actually collecting data yourself, you're the first one collecting the data, how does this work? Well, one of the things you can do is if you have, for example, 5 numbers here that you're collecting data for. Okay, so, and you get 43.2, 41.3, 45.8, 40.1, 46.7. If you take the average of all those, you get 43.42. What level of significance? Well, these are all 3 significant figures, so you might think you round to 43.4. But notice the numbers are bouncing all over the place. We're pretty sure if you take another measurement, what's that next measurement going to be? That's how you find out the level of significance. What's that next measurement going to be? You can be pretty sure it's going to start with a 4. It might be 39.9, but that'd be unlikely. Given this range here, you expect it to be 4. What's the second digit? Well, the second digit's going to be, well, it can be anywhere in this range here. So 43 is right in the middle. What about the third digit? Well, you don't even know what the second digit is. The second digit could be anywhere from 0 to 6. Okay, if you take another measurement, you would really realistically expect it to be somewhere in that range, right? Okay, so that means that these next digits really don't mean anything because you don't even know what the second digit is. So that is your least certain number. The least significant figure is the one you're least certain about. Okay, so you don't even know. Well, actually, you know this is a 4. It's actually the last certain one. The next one is the one you're uncertain about. So that's where your level of significance is. Another way of figuring it is, if you want to be really particular, is find the standard deviation. So the standard deviation of those set of numbers would be 2.83. Okay, so it's about, that can round to 3. So what we could do is, we could say that these numbers here would be, the average would be 43 plus or minus 6. So that's double the standard deviation. You can be like 90-something% sure that the very next measurement is going to be in that range. You're probably like 60-70% sure that it's going to be 43 plus or minus 3. Okay, so you can be pretty darn sure, but this means that there's absolutely, you are almost guaranteed, like 95% accuracy, whatever, that your next number is in that range somewhere between 49 and 37 point or 39.7. You're like virtually positive that your next number is in that range somewhere. Okay, and so that's what we call a 2 sigma variation. You can be pretty darn sure it's going to be within 1 sigma. Okay, one standard deviation. But if you go within 2 standard deviations, you're guaranteed. Okay, your next number, unless something really weird happens, is going to be in there. So that's one of the first things that we do in this lab is that we talk about, well, okay, how do we figure out the level of significance? The next thing that we do is we're going to talk about how do you get from the data to what you're trying to measure. Okay, so for example, if you drop something and it falls and hits the ground, there's a formula for that. the distance that it falls is 1/2 times the speed of the acceleration due to gravity times time squared. Okay, so if I ask you to measure g, the acceleration due to gravity, what do? Well, what most students would do is they take something, they drop it. They measure how long it takes. And they say, okay, so g is going to be 2x over t squared. Okay. Well, the problem is, if you're measuring, what if your ruler was a little bit off? And so the height wasn't right. So every measurement you made had the wrong x. You're going to get the wrong answer. What if when you dropped it, you had reaction time? So every time was a little bit off. Get the wrong answer. You want to find g. You know what 2 is. You better know what 2 is. But if every x and every t is wrong, how do you get the right answer? Well, this is where data analysis comes in. What we know is there's a trend here. X equals 1/2 gt squared. Okay, now if I were to make a graph, okay, there's x, that's t squared. So I measure my time and I square it. So I drop it from a certain height and I figure out how long that takes and I put a dot on here. Okay, then what happens is I measure it from a different height, time it. Okay, so that height, it's going to be this time, square the time, it's going to be there. And for a different height, it's going to be there. For a different height, it's going to be there. What happens is this traces out a line here. Now, you know, equation of a line, y equals mx plus b. Okay. Well, y is going to be basically your distance right here. So that's this x right here is the y-axis. T squared is your x-axis right here. So the slope is 1/2 g. B is your intercept. Now, what happens if your ruler was in the wrong spot? What that does is it changes this measurement here. But every measurement is changed by the same amount, and so your graph goes up or down. Basically, the intercept tells you how far off your ruler was. You get the same answer. You get the right answer. You get the right answer even though every measurement was wrong. What about time? If your reaction time is the same every time, that's going to shift your time by the same amount. So what that will tend to do is try to make your graph scoot back or forth this way. X being wrong makes it go up and down. The time being wrong makes it go left and right. But the slope stays the same. So that means even though every measurement of distance was wrong and every measurement of time was wrong, you could still get the right answer by graphically analyzing it. Whereas if you just plug in the equation, there's no hope of getting the right answer. So this way you get the right answer by looking at the equation and figuring it out. So what if the slope? If the slope was 4.9 meter per second squared, okay, the slope is 1/2 of g. So if the slope equals 1/2 of g, that means g, okay, is going to be twice the slope. Let's do algebra. Okay, so that means if the slope is 4.9 meter per second squared, g is going to be 9.8 meter per second squared. Okay, so this is a powerful tool for analyzing data. It's not just you get the right measurements, but there's a way of getting the wrong measurements and getting the right answer. Now, this doesn't necessarily work if you have random error, but if you have systematic error, this works and gets you the right answer even if you did not know how far off everything was. The slope, the trend, still works. And so that's why this is such a powerful tool. And so that's the second part of the lab, is learning how do you do this. Now remember, the slope has units. In this case, this is distance, this is time squared, so the slope is distance over time squared. If you use, for example, Excel or a spreadsheet of some sort, it doesn't have units in there, it just gives you a number. You need to actually look at your graph, what are you actually graphing, and put the units in. The answer is wrong if you don't have the correct units. So you would have to say meter per second squared is the slope, or centimeter per second squared, or mile per hour squared, or whatever are your feet per second squared, whatever this divided by that is. Rise over run. That's how you do slope. Okay. So here we have data analysis. That's the basic idea of how you do data analysis. The other thing that we ask is, well, how close was your answer to what it should be? Okay. Percent error is comparing your answer to what you know it to be. We actually know what acceleration due to gravity is. That's been measured so well, we all know what that is. You look in the book, you can find out what it's supposed to be. So when you do an experiment, you can actually, verify how close were you to getting the right answer. Sometimes you don't know what the answer is. Sometimes you're measuring something for the first time, and so you measure it, and you measure it two different ways, get slightly different answers. And so in that case, we talk about percent difference. The percent difference lets you figure out how far apart those two measurements are from each other. Percent error is like a measure of accuracy. How correct were you? Percent difference is a measure of precision. How close are your results to each other? So that's kind of what this lab is about, is looking at data, looking at how you analyze data, looking how you tease the correct answers out, even if you don't know whether all your original measurements were exactly correct. That's the power of this. This is why this is so important, because in real life, in real science, in real engineering applications, you don't always get the exact right measurement that you want. You get the measurement you get. So you have to figure out how to get the right answer, even if you're not entirely sure that the individual measurements are correct. And it can be done if you do it correctly. You can actually get the right answer by looking at how things trend. So that's what this first lab is about. So if you have any questions, then you can come to one of the question and answer sessions and ask questions.